Hi, my name's Melanie, and we're going to do a physics problem about springs. There's lots of cool types of springs, like rainbow springs and metal springs. But the best part about springs is that they make really good physics problems. Like this one from 1989, Mechanics number 3. I'm going to show you how to do this problem, and it's going to be really fun. A 2 kilogram block is dropped from a height of 0.45 meters above an uncompressed spring as shown above. The spring has an elastic constant of 200 newtons per meter and negligible mass. The block strikes the end of the spring and sticks to it. The initial contact of the block and the spring would look something like this. So we're going to be doing 1989 Mechanics 3 problem from the AP Physics C test. So part A asks, determine the speed of the block at the instant it hits the end of the spring. So for this, we're going to do conservation of energy. So the initial potential energy equals the final kinetic energy. And that equals mgh equals 1/2 mv squared. And the m's cancel, which then you can move it to make it v squared equals 2gh, and then v equals square root of 2gh. And if you plug in the values for g and h, you get 2 times 9.8 meters per second squared times 0.45 meters. Okay. And 0.45 meters is the height or the distance between the block and the spring before it's dropped. So the velocity when it hits turns out to be 3 meters per second. Okay, so now we're going to do part B. And the question for part B is, determine the period of the simple harmonic motion that ensues. So the equation for the period of the spring is period equals 2 pi m over k. And we can plug in m is 2 kilograms of the block. And k in this case is 200 Newton meters. Newton over meters. Okay, and that turns out to be 0.63 seconds, which is the period. Okay, now for part C. The question is, determine the distance that the spring is compressed at the instant the speed of the block is maximum. So the maximum velocity occurs when acceleration equals 0, and at that time the sum of the forces equals 0. So knowing that, we will set the force of gravity equal to the force of the spring. And we know that mg is the force of gravity, and Hooke's law shows that F equals negative kx. That's for springs. So you set that equal, so negative kx. And then solve for x because we're solving for the distance when the velocity is maximum. So mg over k. And then we're going to plug in values. So mass is 2 kg. G is 9.8 meters per second squared. And it's all over 200 Newton over meters. And then the distance turns out to be 0.098 meters. That's when it's at a maximum velocity. So now we're doing D. And the question for D is, determine the maximum compression of the spring. So for this, we're going to use conservation of energy and set the potential energy of gravity or the object equal to the potential energy in the spring. So that would be mgh equals 1/2 kx squared, which is the spring's potential energy equation. So we do mg and substitute in for h, x plus 0.45 meters, and 0.45 meters is the distance between the original where the block started and where the spring started. And then x is the rest of the distance that we're trying to solve for, the maximum compression. So set that equal to 1/2 k, which is 200 Newton over meter x squared. So we'll plug in more values now. So 2 kilograms is the mass, 9.8 meters per second squared times x plus 0.45 meters equals 1/2 200 Newton over meters x squared. So I'm going to rearrange it to make it like a quadratic equation. So it turns out to be negative 100 x squared plus 19.6 x plus 8.82 equals 0. And if you solve for x, you get 0.41 meters is the maximum compression, and you can get that either by using the quadratic formula or using your calculator. I used my calculator because it's not 1989 anymore. So yeah, that's the maximum compression. Okay, so for part E, it asks to determine the amplitude of the simple harmonic motion. And for this, we're going to subtract the answer to C, which is 0.098 meters, which is also the distance compressed when V is at its maximum, from the answer to D, which was 0.41 meters, which is the distance of the maximum compression of the spring. And this lets you know what the amplitude is, so we can do amplitude equals 0.41 meters minus 0.098 meters. And if you subtract that, you will get A equals 0.31 meters. And that is the amplitude of the simple harmonic motion. So that was Mechanics Problem 3 from 1989. Aren't springs fun?